Hi third grade, I hope you're well. Final class of the week, no Google Meet today. So in the past 2 weeks we've been looking at ions quite a lot, and then obviously the 3 or 4 weeks before that we've been looking at electron structure of the atom. We're going to take a little break from that and we're going to look at something a bit different. Today we're going to look at something called isotopes. So let's go. So we're looking at something called isotopes. So let's have a look at this. So obviously we know this is magnesium, this is the symbol, and we know that there are two numbers here, and these numbers tell us some information. So we know this 12 means that magnesium has 12 protons, and this 12 also means that magnesium has 12 electrons. Well, at least the atom does. We know the ion is different, but the atom, 12 electrons. However, the number of neutrons, does it have 12.305 neutrons? I know I've normally told you to round down. I always say go down to the closest number. But why am I telling you to do this? And is this actually the real number? Let's look at another example. So we've got carbon here. Again, it's got two numbers. So we know here that carbon has 6 protons. And if it has 6 protons, then it must have 6 electrons. But how many neutrons does it have? Does it have 6 neutrons, or does it have 6.011 neutrons? This is what we're going to talk about today. What is going on with these decimal numbers? Because how can you have a point of a number? How can you have half a neutron, or 0.011 of a neutron? How is this possible? So I normally tell you to round up or round down to the nearest integer, which is the whole number. I always say avoid the decimals. And to be honest, you should keep doing that. I don't want you to stop doing that, but I am going to explain why that is technically wrong, okay? So let's look at why neutrons have these decimal numbers. And the reason why is isotopes. Isotopes are different forms of the same element, okay? Different forms of the same element. So let's look at carbon. Carbon here, I'm showing you 3 forms of it, okay? So the really common one is carbon 12, which has 6 protons and 6 neutrons. Another form is carbon 13. It has 6 protons and 7 neutrons. And another form is carbon 14, which has 6 protons and 8 neutrons. So notice how in these 3 different forms of carbon, they have a different number of neutrons, 6, 7, and 8. These are called isotopes, okay? Isotopes, these are different isotopes of carbon. Carbon 12, carbon 13, carbon 14. And what makes isotopes different is the number of neutrons, okay? And as you can tell, most carbon here, you can see 98.9% of all carbon is carbon 12. But there is a percentage of other forms of carbon. So 1.1% of carbon 13 and less than 0.1% of carbon 14, okay? And there'll be other forms of carbon as well, but these 3 are the most common, okay? Just wanted to show you here that this is the carbon element. So the question is, why does it have 12.011? Well, the reason why is this number here is an average. It's an average of all the different forms of carbon, okay? We don't want to just have on our element just one carbon, because if you have a block of carbon, let's say you have, I don't know, a kilo of carbon, well, 98.9% of that will be carbon 12, 1.1% will be carbon 13, and 0.1% will be carbon 14. So this mass number here is an average, like promedio, an average, okay? So this 12.011 shows that you can see it's very close to 12, and that shows because 98.9% of carbon is carbon 12. But these small percentages of carbon 13 and carbon 14 pushes the average up a little bit, okay? So just to repeat, isotopes are different forms of the same element, and what makes them different is the number of neutrons. Let's look at another example. So here we've got lithium, okay? And here we've got 3 forms of lithium. We've got lithium 6, lithium 7, and lithium 8. And as you can see, each one has 3 protons. And if it has 3 protons, each one has 3 electrons. And you can see that here. The 3 electrons, which are the red ones, 3 electrons, and 3 electrons, which are the red ones. Let's look at the protons. 3 blue protons, 3 blue protons, 3 blue protons. But what we have in these different isotopes is a different number of neutrons. In here, lithium-6 has 3 neutrons. Here it has 4 neutrons, 1, 2, 3, 4. And here it has 5 neutrons, 1, 2, 3, 4, 5. Okay? So look at this one, 6.941. Which one do you think is the most common? The most common one is the number which is closest to. So 6.9, is it closer to 6, 7, or 8? Well, 6.941 is closest to 7, which means lithium-7 is the most common isotope of lithium. But other isotopes of lithium exist. Lithium-6 exists, lithium-8 exists. But the most common one is lithium-7 with 4 neutrons. Okay? How can this be useful? Actually, there's one technique which is incredibly useful and uses isotopes very effectively to determine how old an organism is. So let's say we have an organism which has died, or one that is still one that has died, and we want to see how old it is. We can do carbon dating. Now, carbon dating has a limit. Normally, we cannot see organisms that are over 50,000 years old or died 50,000 years ago. Can't work on something living, but once it's dead, we can do carbon dating. But normally the limit is about 50 to 60,000 years. So you cannot do carbon dating on a dinosaur fossil, for example. But something like a woolly mammoth, you could do. So carbon dating. And the reason why carbon dating works is because of carbon-14, okay? So all organisms have carbon in them, and a percentage of that carbon is carbon-14. It's a small percentage, but it's normally quite a definite percentage in living organisms. Right now, in your body, you have carbon-14 inside you. Most of the carbon inside your body is carbon-12, but a certain percentage will be carbon-14. Same for all living organisms on the planet. When we eat, like we're eating vegetables, we're eating carbon. Okay, plants are made of carbon and we eat that. However, when we die, we stop eating, obviously, so we are no longer ingesting carbon. So what happens is the carbon-14 in our body slowly decays into carbon-13 and carbon-12. Now, we know how long it takes carbon-14 to decay. Carbon-14 has a half-life of 5,730 years. So we can calculate how old a bone will be by identifying the percentage of carbon-14. We know how much carbon-14 is in a living organism, and then the carbon-14 which is currently in the bone, we subtract it from what that original total would be. So let's have a look at this bone here. The organism has recently died, it's stopped eating, but it's recently died, so it has 100% of its carbon-14. However, 5,730 years later, 50% of the carbon-14 has decayed. So if we find this bone and it only has 50% of the carbon-14 that it should normally have if it was living, then we know that this bone is approximately 5,700 years old. Again, if we find a bone which has only 25% of the carbon-14 that it should have, then we know that this bone is approximately 11,500 years old. And the same thing again, okay? Now, if we get a bone which is around 17,000 years old, it will only have 12.5% of carbon-14, okay? So looking at this can give us a pretty good idea about how old certain things are. Really, really important in archaeology. There's actually a really good exhibit at the Museum of Anthropology. I'm sure many of you have been in what part of the city is that in? It's on Reforma. I can't remember the name of the station, but you know, on Reforma, there's the Anthropology Museum. Really, really good, and it has a really, really great exhibit explaining what carbon dating is, how it works, and all the different ways they have used it to identify how old certain things are that they have found. So here is your question about isotopes, guys. You've got two options. You can do it on a Google Docs and upload that docs to Google Classroom, or you can just write your answer in a private comment on Google Classroom. For me, that's fine. First one, you've got to do a little bit of calculating. So we know carbon has 12, 13, and 14 forms, okay? If this is sulfur, 32.066, I want you to estimate, which is guess, adivinar, and write down two forms of sulfur. If you know that sulfur is 32.066, and this is an average, you must know at least two forms of sulfur which exist. Different isotopes of the same element have a different number of which subatomic particle. So which part of the atom makes isotopes different? Why do we write this number as a decimal? 4. What is carbon dating useful for? And finally, question 5, you might have to investigate on the internet. Deuterium is the special name for an isotope of which element? Guys, that's the end of the video today. I look forward to marking your answers, and I hope you have a great weekend. Take care. Bye-bye.